Hello there. I would like to briefly introduce a project I've been working on for a while, which I am calling BuzzKill. I call it that because for most people who are making a small microcontroller project and get to the point where they want to add sound, it's pretty common to just connect either a piezo or a speaker to an output pin and send pulses through it at various frequencies. So basically what you might call buzzers. Of course, other options are available for sound output, but they're generally based on playback of pre-recorded samples, WAV files, MP3 files. It gives a very high quality sound, but you lose flexibility. You can only play sounds that you have pre-made and pre-installed. So there's no ability to create sounds dynamically tied to maybe a sensor reading or some current condition. Which brings us back to buzzers and making sounds from scratch. I want to provide another option, one that can replace the poor buzzers with something much more powerful and, well, pleasant. The idea is that almost anywhere you might attach a buzzer, you can attach a BuzzKill instead and get a lot more options without any more work. Let's talk briefly about the hardware, which as you can see is very simple. All the magic, so to speak, is in the software, which is running on this little chip right here, which is an Atmel DD series, chosen for its low cost versus performance, which is perfect for this application. One of my primary design goals was a very low cost of hardware, and I think I succeeded in that pretty well. Besides the normal external crystal and capacitors for the BuzzKill chip, the only other hardware component is a Class D audio amplifier right here. This one is a pre-made one from Adafruit. Strictly speaking, it's optional. We could just connect the speaker directly to the chip here, but it gives us a lot more output power, and after all, good audio is only good audio if somebody can hear it. And plus, I think if there becomes a standardized BuzzKill board, whether it's an Arduino Shield or a separate breakout board or what have you, it will probably have amplifier included with the chip all on one board as a single standalone unit. Being driven by the amplifier, we have a very basic, small, cheap speaker, the kind you see very commonly, which is why I chose it for testing, even though it's not really a very good speaker for good quality sound. It really struggles with any low frequencies, basically makes everything sound thin and tinny, but it's pretty representative of what many people are working with from either size constraints or cost constraints or both. I just have this one literally taped into a roll of tape just to orient it vertically toward the camera and microphone. And by the way, volume here has not been a problem at all. I've actually turned the amplifier way down to a pretty low level, because otherwise at this distance things are just too loud. At the other end of things, we have the BuzzKill chip attached to an Arduino Uno. This is not actually part of the BuzzKill circuit proper. It's just here to play the part of a controller and send the desired commands. The BuzzKill itself is a peripheral, so it needs something to give it instructions on what to do and what sounds to produce. Obviously, Arduinos are very popular, but this could be any kind of microcontroller or something like a Raspberry Pi, whatever you want to connect it to. It's connected through either an SPI interface or a TWI interface, which is what Atmel calls what other vendors would call I2C or I2C. That's what I'm using here for this connection. So I just have two wires right now connecting the BuzzKill chip over to the Arduino. Now let's go back to the output side where I have a scope attached so you can see the waveforms visually. Anybody familiar with music synthesizers will immediately recognize most of these. There are four waveforms that are considered fundamental for sound synthesis. This one is a pulse wave. I'm starting with this one because it's the only waveform that you can do from a buzzer or a PWM speaker setup, you can hear the characteristic sound that you're probably used to. Even though it's not a very pleasant sound by itself, it's still a very useful waveform and is used in a lot of mixes. But to do that, you really need to be able to control the pulse width. And usually libraries, especially Arduino libraries that I've seen, don't let you do that. The tone library, for instance, doesn't do that. The Arduino can do it at a hardware level, but it takes a bit of work. You have to do it manually, or the software just skips it for some reason. I'll quickly show what I'm talking about. The wave currently is at 50%, which technically makes it a square wave. I can change that, let's see, to a 25% wave. And you can see on the screen now what changed, and you can hear that the tone changed a good bit too. Now I'll switch to a sine wave, which is the most fundamental wave. There we go. Notice how clean it sounds compared to the pulse. That alone is enough of improvement over buzzers, I think. I'll point out one unusual feature here, because otherwise it's just a completely normal sine wave. But the same width adjustment we did before with the pulse wave, we can also do here. In fact, we can do it for any waveform. But here it really shouldn't be called a width adjustment, more like a midpoint adjustment. And let's see, same as I did before. And you can see the effect that it has here is a little bit different. I set it to 25%, so you can see what it actually does in this case is compress the positive portion of the wave and expand what's usually the negative portion of the sine wave. And I can do the same thing the other direction. Instead of 25%, if I go to 75%, now we see that it's expanding the positive portion of the wave and compressing the negative portion of the wave. There are two more fundamental waveforms that I'll show very quickly since they're probably familiar. Let's see. This is a ramp or a sawtooth waveform. People use both terms. And here is a triangle waveform. I think the name on that one is pretty self-explanatory. And then we have a noise waveform, which is useful for percussion sounds and sometimes just adding randomness to other sounds and in mixes. Now I have a couple of unusual waveforms that you don't normally see. This one doesn't really have a name. It doesn't sound like too much, on its own, but it's very useful as a modulator for other sounds, like siren or vibrato effects. And then finally we have an exponential wave. And again, it's not very pleasant on its own, but a very useful shape for modulating other sounds and doing amplitude shaping on other sounds. So those are all the predefined waveforms. There's also a custom waveform that you can define however you like, but I can't really show that here because basically it just looks like anything you'd want it to. But I'd also like to show a couple of other manipulations you can do on waveforms, and these apply to any waveforms, but it's easier to see on the exponential waveform that we have here. First, let's see, we can invert it, which essentially means to flip it in a vertical direction. We can also reverse it, which essentially means we're going to flip it in a horizontal direction. And finally, we can add a step function in case we don't want a smoothly rising or falling curve like that, but we want something with more discernible steps to it. And again, we can apply all of those to any waveform we choose. Now, I've mentioned a few times about using a waveform to modulate a sound. I'll show you a quick example. First I'll set this one back to a sine wave. Now, of course, it's static in terms of its frequency and amplitude, but I can use another oscillator to modify the sine wave in various ways. So, for example, I can modify the frequency like this. So now I have one oscillator modifying the frequency of the audible oscillator. Now I can also modify the amplitude. Let's see. There we go. So now we have a sine wave being produced, but its frequency is being modulated by another oscillator, and its amplitude is in turn being modified as well. So you can get pretty decent like siren type sounds, warbles, things like that with just a few commands. And you can add a lot more, different kinds of modulations to create some really interesting sounds. Like, let's see. Like that one, for instance. That's using a random frequency modulation on a bass sound, plus an amplitude modulation as well. That's just going to keep playing forever until I stop it, so let me go ahead and give that a reset. Okay. Well, speaking of amplitudes, I haven't mentioned anything about envelopes. Won't go too much into them here because it's a very big topic all by itself. A lot of you may already know about them. If not, they're pretty standardized. There's a lot of information out there about them, and the way the BuzzKill implements them is really a very standard manner. Specifically talking about what are called ADSR envelopes that control the volume contours around individual notes in a sound. For example, here is a simple note with no envelope applied. See? Okay, it's just the same volume from start to finish. Now if we add an envelope around it, same note with an envelope, see how it kind of grows in and then fades away. That usually makes notes sound much more natural. All natural musical instruments have some kind of envelope associated with them. So when we hear sounds with no envelope, it tends to sound very electronic and artificial. I'll play part of a song now, and you can see and hear how the volume changes help accentuate the individual notes and make it sound more like natural musical instruments. Now for this, it may seem strange that after showing all the cool alternate waveforms that we can do that buzzers can't do, for this I'm going to go back to the pulse waveform. But I'm doing it on purpose to highlight just this one particular feature, the envelopes here, while doing everything else the same way that a buzzer would. Like a science experiment where you only change one variable at a time. So let's give this a go. And have a listen. Now I'll play one more song to illustrate a final element that I haven't discussed, which is layering or mixing multiple voices. A buzzer only makes one sound at a time, but with BuzzKill we can have up to 4 separate voices all playing at once, which is really helpful for richer sounds. Just like before, I'm going to stick with a pulse wave form for the main melody, but the extra voices you'll hear have some variety, since that's the part I really want to emphasize with this one. Here we go. Now this video is already going longer than it probably should, so I'll quickly go through the final feature, which is speech. There's several speech products out there, and really for the most part they're going to produce superior speech to what we can do here. This is a very simplified speech synthesis. It's not going to win any awards for realism, but that wasn't really the point. If you want high quality human level speech, you need to get something purpose built for that and be willing to pay for it. But I'm pretty happy with what I've been able to squeeze in here alongside all the other sound production possibilities. So maybe I should just call it a producer of speech-like sounds or something like that. Anyway, here's a basic sample. So there's lots of adjustments we can make on top of that, speed and pitch being the simplest. There's a lot of others as well. I'll adjust the pitch here so you can tell the difference. And we can also, the speed and they're completely independent, so I can slow it down while keeping the higher pitch as well. Like I say, there's lots of other adjustments we can do that as well, but I'll go ahead and end things here. The video was just meant to be an overview of the important features of the BuzzKill chip, not a demo of every cool sound that it can make. But hopefully it's given you an idea of how it can be used and what possibilities it can add to a project, and how it can replace the venerable buzzer with very little extra cost or complexity. Thank you very much for watching, and good luck with whatever your current project may be.